So let's do an example problem here. This problem says a clean, recently completed earthen channel with a Manning's N of 0.017 is to carry 500 CFS of water on a 0.0001 slope. Find the most efficient cross-section dimensions for a rectangular channel. Okay, so we start with the knowledge that for a rectangular channel, we've established this in the previous video, A equals 2y squared, R equals y over 2. We write out Manning's equation, Q equals 1.49 over n, A r to the 2/3, s sub 0 to the 1/2. Another way of saying A equals 2y, well, these are A and R in terms of y. We can also write A in terms of B, which is B squared over 2 for A, and R was B over 4. So we now plug in everything we know. For Q is 500 CFS. That equals 1.49 over 0.017. And then for A, we're going to plug in B squared over 2. And for R, we're going to plug in B over 4 to the 2/3. And then our slope is 0.0001 to the 1/2. And we want to solve this for B. And because we've put these relationships for A and R into Manning's equation, these relationships were based on this assumption of most efficient cross-section, which got us down to R equals y over 2, and then from there we could derive these relationships for A and R. So if we solve for B here, that should be the most efficient cross-sectional shape. Now I can reduce this all down, and I actually can solve for it explicitly. It winds up being 500 equals 0.1739 B to the 8/3, and B winds up being 19.82 feet. And since y was equal to B over 2 on the previous page, y is 9.91 feet. So here's our channel. B equals 19.82, and our y is 9.91 feet. Thus, our cross-sectional area winds up being BY 19.82 times 9.91, or 196.5 feet squared. Now, this is an earthen channel, it says in the description. We've now solved this problem. We've computed the most efficient cross-section, but let's say we had an additional constraint. And that additional constraint, we'll put it in black, was that our Vmax was 2 feet per second. If we have velocities faster than that, we get erosion in the channel and it's not stable. So we need to limit the velocity to 2 feet per second. So we can now calculate our A min is Q over V max, which is 500 over 2, or 250 feet squared. So our minimum cross-section area has to be 250 feet squared, but our area that we computed was only 196.5 feet squared, so our velocity is going to be higher than our maximum allowable velocity. So at this point, we basically need to constrain ourselves to that cross-sectional area of 250 feet squared and say if we get to that, if we're at 250 feet squared, then we've minimized our cross-sectional area, and we just need to calculate what the dimensions of the channel under that case would be. And so for that, I would rewrite Manning's equation: 500 equals 1.49 over 0.017. My area would be 250 feet squared. I'd put my unknown r to the 2/3 in, and then 0.0001 to the 1/2. And now I just have to calculate what r is, and since r is the area over the wetted perimeter, and I know the area, that'll give me the wetted perimeter. And so if I do all that, I wind up with r equals 3.45, which is area over wetted perimeter. I can solve for the wetted perimeter, which is 72.5. And now I need to solve a little system of equations that says my area, which is 250, is equal to by, and my wetted perimeter, 72.5, is equal to b plus 2y. So two equations, two unknowns, and I can solve for b and y. And if I do that, I actually get two solutions: b equals 7.7, y equals 32.5, or b equals 64.8, y equals 3.85. So one of these, this one has a pretty narrow channel that's really deep. This one's a really wide channel that's very shallow. Either of these is acceptable, but this one would probably be easier to construct since you're not digging down 30 feet into the ground. So that's how you do one of these problems. One of your homework problems is going to be to do the same sort of thing, but with a trapezoidal channel. One other thing I'll note is that I said earlier that your Q is usually constrained, which it is, and your N, you can choose the material the channel is made out of, but typically it's fairly constrained for the application. The S sub 0, if you need to make a shallower slope, sometimes you can by, that slope is the fall of the channel over some distance. And the distance is the distance of travel. It's not the distance sort of as the crow flies. So if you needed to shallow up the slope, you could kind of snake your channel around, add length to it without changing the vertical drop, and so you'd be shallowing up your slope a little bit. And that'll make your channel a little deeper. It'll change the dimensions a little bit. So sometimes you want a winding channel if you're designing a natural looking channel, a stream or something like that. Then you want it winding. There might be other cases you want it winding too. You need to avoid some obstacles or something like that. So you can take that into account in your slope variable.